So buffer capacity is really this fundamentally important parameter for buffers, which is really the how much acid or base can you add to this thing and it still behave as a buffer. In other words, how much can you add and it still resist a change in pH. And so the specific definition of buffer capacity is actually the amount in moles of this strong acid or strong base, H plus or H minus, to change the pH of that buffer solution by 1 unit, plus or minus. And so you could have a buffer capacity in the basic direction, which is how much hydroxide you need to add to change it by 1 unit, or you could have it in the acidic direction, how many protons you need to add to change it in the other direction by 1 unit. And so let's set up an example. So let's use acetic acid acetate as the buffer system here, which has a pKa of 4.74 and a total buffer concentration of 0.1 molar, and the buffer has a pH of 4.5. And we want to figure out what the buffer capacity is in the basic direction. In other words, how many moles of OH can we add to this buffer solution before it changes by 1 full pH unit. So before we can figure out that buffer capacity, we should start by just writing up a Henderson-Hasselbalch equation and figuring out what are the ratios of acetic acid and acetate at pH 4.5. Then we could do another Henderson-Hasselbalch at 1 pH unit greater at pH 5.5 and see how the ratio of acetic acid acetate buffer have changed, and that will allow us to figure out how much base was added. Okay, so if we start with our initial pH of 4.5 before we've added any base, and we just want to figure out what the ratio is, we just pop that into the Henderson-Hasselbalch with the known pKa of 4.74. We get a ratio of 0.575, and then I just rewrote this as an expression. We know what the total buffer concentration is, 0.1, so I could figure out what is the actual concentration of HA and A minus at this pH. I just need that second equation, which is just the sum of HA and A minus add up to that total concentration. Now I can use these two equations to substitute and solve for the respective concentrations. And that gives us the two values of 0.0635, and that's molarity, and 0.0365 molarity for A minus. So those are the concentrations of the acid and conjugate base when we have the starting pH of 4.5. But under the perturbation of this buffer capacity problem, we're being asked, well, how much OH needs to be added to get this thing to shift from 4.5 to 5.5. And so that would allow us to rewrite this Henderson-Hasselbalch equation, but replace the 4.5 with 5.5. So I've rewritten this Henderson-Hasselbalch equation with 5.5 here. 4.74, the pKa is unchanged, but now my ratio, of course, is going to change here. And the direction of change is either plus some amount x or minus some amount x. And remember, this is A minus over HA. So how do we know which one's plus and which one's minus? Well, we're adding base, right? So if you're adding base to this system, what's going to happen? What's going to react with the acid? And if it reacts with the acid, it means it's going to destroy some of that acid. That would be a minus x. And in doing so, it's going to be creating more of the conjugate base. That's a plus x. So that's why you see the plus x on the top, because it's creating more of the conjugate base. And you see the equal and opposite minus x down here, because in order to create that x, it's got to be removed from the existing amount of HA. Okay, so doing some moving around here, we're going to get something that looks like this. We're trying to solve for x, so 10 to the 0.76 is equal to this ratio. So the 10 is just getting rid of that log base 10 here. So we'll take it one step further. Simplifying looks like this, so that whole term equals 5.75, so I can multiply the denominator here, get that on this side, and we get something that looks like this. Okay, so keep solving for x, and you get something that ultimately is x equals 0.049, and these are units of molarity, so moles per liter. And the definition for buffer capacity is the amount of moles of protons or OH needed to change pH of buffer by 1 unit. And I should be clear here, this is for 1 liter of a buffer solution. So 1 liter of solution. And why that's important is because we just computed this in units of molarity, which is the same as 0.049 moles of OH per 1 liter. And so this is the answer. So the buffer capacity in the basic direction is exactly 0.049 moles of that hydroxide per liter. If we wanted to, we could have done this the other direction. We could have said, what is the buffer capacity in the acid or acidic direction? Everything would have been the same on the front end. The only thing that would have changed is instead of in the second step where we had our original pH plus 1 unit, we would have had original pH minus 1 unit, so we would have replaced 5.5 with 3.5 and then solved the expression the same way, and we would have ended up with moles of H plus per liter, and that would be a proxy for how much capacity that buffer has to resist a change in pH. The larger the number, the higher the buffer capacity in that direction.